So I'll say welcome back everyone to PCB Design Fundamentals Part 2. As you heard, Matias had a few questions. His first question had to do with when you're actually routing, and we're going to talk about this a little bit more, probably actually this Wednesday when we get to some more hands-on with the tool itself, since we only got to creating the design rules last week. Um, but um, SMT pad, through hole pads, do's and don'ts of how you route the trace into or out of the pads. The two main rules are no acute angles and no reducing of the trace of the clearances between the pads. So those are our two main rules that we're going to follow there. His second question had to do with grid versus gridless based routers. And now that I have the recording started, I can actually give you a little bit of the history of printed circuit board design. Okay, so way back when, before we even had computers, we used to route our printed circuit boards on panes of glass. It was very special glass that had grid lines etched into it, and you used to use pieces of colored tape, red tape and blue tape. This is why we consistently use red and blue to represent our top layer and our bottom layer. It has to do with photolithography processes, and when you shine red light through the red traces, they turn black and everything else is invisible, and the same thing with the blue. So you could do that. So basically, we'd have pieces of cellophane type tape that were exactly the width we wanted, say like, or the scaled value of the width we wanted, like 10 mil, 20 mil, 25 mil, whatever it was. And so you would literally lay the tape along those grids. And by having a known width tape and a known grid width, you knew what your clearance was, right? Your clearance was the grid width minus one tape width, because half the tape width was on one line, half the tape width was on the other line. So it was whatever the grid size was minus one tape width. And that's how we do that. And so the early days, early computers, like late 70s, early 80s, when a lot of it was you didn't even have a monitor, you literally had just a printer or a plotter. Same thing. Early computers that did not have the processing power of modern computers, rather than creating design rules the way we are now, you would simply have a width, a line width defined, and by routing on the grid, again, you knew you met your clearance requirements without actually having to have a clearance rule defined. With modern tools, all the big three, Cadence, Mentor, Altium, plus all of the second tier tools, KiCads, dip traces, etc., all now support rule definitions. As long as you're meeting your rules, there is no reason to route on a grid. Now, grids are great for placement, but for routing, I always route as gridless as I can. I typically leave it on a 1 mil grid in my system, and that's usually sufficient. Because again, I want the tool to meet my design rules so I can get the higher density as we do smaller and smaller devices, smaller and smaller boards, higher and higher density where parts are packed in tighter and tighter. The need to have to be able to use a grid-based router, a grid-based routing system causes us to actually lose some of our available area of the board because of the grids. And I'll actually remind me on Wednesday, Mattia, and I will actually demonstrate how that will happen.
Okay, right. Thanks for the answer. The next one was regarding the overlap of the silk screen with vias, pads, or other silk screen
Yes.
to be avoided as much as possible, or kind
So
of don't care.
silk screen to silk screen, don't care. That's completely up to your personal aesthetic of your organization. Vias and pads, however, um, your fabricator, even if you put the silk screen on the pad, your fabricator is going to clip it off. Um, any surface that needs to be a solderable surface, such as through hole or SMT pads, or if you have a via that is not covered, like tented, then yes, they will clip that because the silk screen on pads is a contaminant that will prevent a proper solder joint formation. So no silk screen on surface mount pads or through hole pads for soldering. Vias if the solder mask is exposed. Basically, If I have an opening in the solder mask, there shall be no silk screen there unless I explicitly tell my fabricator I am intentionally doing that.
Okay, okay, thanks.
Mm-hmm.
The next one is regarding the via placement when we are, let's say, overlapping them with the SMT pads.
Mm-hmm.
And here the question is this something which is allowed, or we should avoid it because to kind of prevent that the, let's say, solder is taken away from the pad and
Yes,
kind of
we
sucked
call
into the
that
via?
solder thieving. And
Mhm.
yes, we should avoid solder thieving. However, and we're going to get into this a little bit more when we get to manufacturing as well as in signal integrity. As long as we have covered that via with the solder mask, so the solder can't be thieved, or in the case of like a micro via, which we'll talk about a little bit, it's normally covered in my advanced design concepts class, but we're going to do a little bit of micro via in this class, uh, or a blind via where the via does not go all the way through the board, only goes a layer or two down. Now it's more of a dimple than a full through via, and you will not steal that much solder, and you can mitigate or compensate for that. So there are pros and cons, but yes, in general, for the purposes of this class, we do not want to allow what we call solder thieving, and that is not just vias. That is any additional copper feature larger than the defined copper pad. And again, we will have examples of that coming up here when we start getting to the main board routing. I will show you some cases of that where we will do things like extend the copper area of the tab of our big heat, our big voltage regulators, act as a low inductance and good thermal conduction path so we can get the thermal energy and current out of the device and into the plane layer as fast as possible while still preventing the solder thieving. And we'll walk through how to do that.
Okay, cool. The one, I have only two more, and one is regarding caps, and one is regarding the rooms or the use of rooms for, let's say, non-repeatable structures. Is that
Uh-huh.
something we should, let's say, keep and then extend it over the entire PCB if in case the components are, let's say, stretched out and you cannot really group them? Or is it okay to delete the room if you are actually not needing
So
it?
the deleting of the rooms is a personal preference after you've done your placement. My issue with that is every time you delete a room and then you have a revision update, right, that basically says, oh, I need to make a change to my design, I need to change a resistor or add a little bit of, I need to add an RC pole to something. Every time you do an update from the schematic, it's going to try to put those rooms back in anyways. So instead of deleting rooms, I simply make them invisible. I turn the little eyeball off so they're no longer visible, even in rooms with repeated. After I've repeated the room and placed them where I want them, and I'm going to do my main board routing, I just make the rooms invisible. So the deleting choice is that's a deleting versus just leaving them there. That's a personal choice. I will also show you how you can use rooms for other features in the tool other than just placement. They actually allow you to create area rules. We are going to use an example of an area rule when we get to our BGA, where we're going to allow narrower trace widths and or smaller clearances only in the area of our BGA. So there are other benefits to leaving the room in there, even if you have it invisible. Um, so I personally leave it there. Now, should you extend it over the whole board? All I usually do is if I'm going to do anything with that, just right click and say wrap a non-orthogonal, uh, you know, wrap an orthogonal or even a non-orthogonal room. So it's a weird shape rather than a full rectangle. But again, once I've done that, I just make the rooms invisible when I'm ready to do my route.
Okay, I had no idea you can hide them, but that's a great piece of information as well.
Yep.
And the last question is regarding the caps. As I said, if you could maybe elaborate a little bit. I saw that in some places we have, let's say, double decoupling caps.
Uh-huh.
So let's say why use two caps? Any rules of placement? Let's say
We're going to get
should we
into
do them
all
inline?
of that
Ah, okay.
in signal integrity. That is all
Perfect.
about signal integrity. And the reality is that all of those physical caps for power pins for modern digital circuits, I'm going to qualify this. The statement I'm going to make has no bearing on analog circuitry at all. On analog circuitry, the old rule of thumb, put that capacitor as close to the power pin is absolutely true. On modern digital circuitry, and we'll get into this in silicon geometry. In fact, I'm doing a professional development course on this at Apex this year. If any of you guys are coming down to Apex, the reality is, because of the shrinking geometry of the silicon inside the digital chips, every single one of those physical capacitors by the power pin of the digital chip is completely useless for the instantaneous switching needs. All those physical caps are doing anymore is providing charge into the plane pair, and we'll get into all of that moving forward. Now, why am I using multiple caps? We'll see that also in signal integrity. It has to do with the self-resonant frequencies of the individual caps, the real models of the caps, and helping us to maintain a maximally flat, minimal impedance response to instantaneous switching current across all possible frequencies. And we'll see why that is here moving forward shortly.
Thank you very much for the answers. That's all. Thanks.
Yep, not a problem. Great questions. Any other questions out there this morning, guys, before we get started on today's slides? Yes, looks like Kevin has a question.
Yeah, is that also like when you say like the power pins and the caps aren't doing anything for the high-speed digital signals nowadays because the silicon die shrink? Is that, I mean, we're talking like the 0201 caps as well? Like those aren't doing
01,
anything?
005s, 0201s, they do nothing. There is, and we'll get into why that is, and it has to do with that term I just used called self-resonant. Every physical capacitor in the real world, for every physical capacitor you put on your board, you get a free resistor and a free inductor because of the manufacturing of those parts. As soon as I have an RLC circuit, for those of us that took electrical engineering, we recognize that as self-resonant, which means there's only one small frequency at which it's minimally flat. Otherwise, at any other higher frequencies, it's either acting inductive or capacitive and still a high impedance, and it does not respond fast enough. The only structure of our circuit board that's going to be able to respond fast enough to the instantaneous switching demand is the capacitor made out of the plane, because it has near zero resistance and near zero inductance because of the process of manufacture. And therefore, the physical capacitors we put on our board are really only going to be there to refill the charge in the plane capacitor, because the plane capacitor can respond fast enough, but it'll never have a large amount of capacitance to hold a huge amount of charge. So it constantly needs to be refilled. That's where our physical caps come in. We will refill the plane from our physical capacitors.
Okay, so would you agree with the statement that like the physical capacitors on the board maybe help you up to 100 megahertz, and then after that it would be the plane capacitance in the
I'm not
PCB?
going to say any frequency, because any
Okay.
specific frequency is dependent solely on the structure, the size, the capacitance, the capacitive dielectric material, et cetera, et cetera. Each and every physical capacitor has a unique self-resonant point, and that is the only point, that is the only frequency where that capacitor helps.
Okay.
Below that frequency, it's high impedance because of capacitive reactance. Above that frequency, it's high impedance because of inductive reactance. There's a single except for your bulk, which are your tantalums and electrolytics, every other physical cap you put on the board has a single very narrow frequency range at which it is even responsive at all to
Right.
switching demand.
So I guess last thing would be, is this is probably why it's really important for the silicon manufacturers to make sure that they have enough hold up capacitance on their local PCB, like that they make the die on?
Not entirely. That's a
Okay.
great question for outside of class.
Right.
Or bring it back up when we get to silicon. I'm sorry, when we get to signal integrity, not silicon integrity. Signal integrity discussion.
Okay, thanks.
All right. With that, any last questions before we go? These are some great questions, guys. Any other questions before we begin? All right. in that case, let me go ahead and get started with today's slides. Sorry, it's off my screen a little bit here. So first week and last week, we talked about some of the basics and advanced design concepts. Today, we're going to start talking about the materials. I've talked about this a little bit before. We'll go into that. So the basic materials that we use for our bare board itself are going to come from the IPC 4101. This is the printed board laminates for multi-layer, double layer, and multi-layer rigid organic PCBs here. Right now, there are other standards as well for things like flex materials or for specialty things like the high frequency RF and so on, where we start getting into the exotic materials, the Teflons and thermoplastic and so on. But for the most part, these are going to come from 4101. 4101 includes sheets of woven reinforcement impregnated with a bonding resin. The individual slash sheets within this specification will define the specific configurations. And the specs describe the mechanical and electrical performance requirements for all materials used in the rigid boards. And you know what? If you don't mind, I'm going to fix something here because this constantly looks like a double sheet. Let me copy that. Go up a page. Let me just drop that fourth bullet right here. And just delete that one. There we go. Sorry. That's been bothering me for a while. Don't know why I did that way. So there's our four statements there. So what are some of the requirements of the materials of the board itself? Well, those might include physical requirements such as CTE, cladding type, cladding thickness, dielectric thickness, electrical requirements such as electrical strength and permittivity, chemical requirements, glass transition temperature, flame retardant rating, flammability rating, and I should have made a note here. This is not an exhaustive list. This is a partial list of those. There are further additional requirements that are defined for these materials, but these are some of the key requirements that we're going to look at here. Okay. So some of those physical requirements, such as CTE. CTE, as we all know, should know, stands for coefficient of thermal expansion. That describes the rate of change of a dimension of the material due to a change in temperature. Also can be thought of as a change in physical dimension due to change in temperature. It's going to be different in each axis due to the directionality of the fiberglass. Whenever you have a woven material, whether that's woven metal in the form of like the rebar that we use for reinforced concrete, like in our roadways, whether that is the woven cotton that we use to cotton or nylon or rayon or wool or whatever we make our clothing out of, whether that is woven glass that we use for fiberglass for the body of our vehicles or surfboards or skateboards or whatever material, or in this case, our printed circuit boards. Whenever I have a woven material, the act of weaving those fibers together means that you can only stretch that material so far in the direction of the weave. So you have this XY direction of a weave pattern, which means if I pull the material in either X or Y, it can only move so far because of that woven nature of it. Whereas in Z-axis, if I put two sheets next to each other, then what I end up having is I can separate the two sheets from each other by however much I want or by a much greater distance because I don't have a woven material between the two sheets. I only have the woven material on the one plane, on the XY plane. Okay? So we say the different in each axis due to directionality of fiberglass, with X and Y axes being similar, Z axis being different. Typically, it's going to be measured in parts per million per degree C, but sometimes in percent per degree C. And as an example here, and again, I'm using English imperial units here instead of metric. The math would work out exactly the same regardless. And as an example here, if I have a printed wiring board that is 100 mils thick at room temperature of 25 degrees C and a z-axis CT of 100 ppm per degree C, if the board is then increased in temperature to 100 degrees C, the thickness of the board will increase from 100 to 100.75 mils, or almost 1% here. And we will see that right here. So the way we do that, we start with the room temperature board thickness, 100 mils. We then take that dimension, divide by 1 million to get 1 ppm, or part per million, multiply by the number of parts per million. That is my percent of change due to each degree of temperature, multiply, and then I'm going to take that. So that's my 100 ppm right there. Then I'm going to take my total delta T. I take my final temperature, subtract my starting temperature. That's my delta T. Multiply that number by the parts per million value right here. And then I add that value to my initial starting temperature, and you'll see I get this value right here. Note that this system here works equally well for cold temperatures, right? So let's say, for example, that I cooled my board from 25 degrees C to minus 50 degrees C, right? So I would have negative 50 minus 25, which would give me negative 75. Instead of increasing to 100.75, I would reduce to 99.25. I would literally subtract 0.75 mils. So the rate of change is the same regardless of temperature, whether you're heating or cooling. Okay, so that's a little bit about CTE. Then we have descriptions of the cladding type. So cladding types. The most common cladding we're going to use is copper. But even then, there's multiple types of copper. The most common copper we are going to receive on our printed boards is what we call electrodeposited. This is where the copper is held in solution. So the copper ions are dissolved in solution. The fiberglass and resin material, the core material, is then rolled through that fluid and then through a electroless deposition process or even an electrodeposition process. Copper will then be deposited onto the surface of that material, at which point the copper will then have a much thinner, tall, vertical crystalline grain structure. So it's a simple, basic electro or electroless deposition process. Okay. Now, we also have different treatment methods. These treatment methods here are how we're going to roughen the surface, usually oxides or other treatments. And these treatments will roughen the surface to allow bonding to happen on other layers as well. Okay. Now, that's the most common. But then we have the rolled annealed as well as the wrought copper and various combinations thereof. So, quick little side tangent here. Whenever a mechanical engineer or machinist or whatever talks about a wrought metal, does anybody out there know what it means for a metal to be wrought? W-R-O-U-G-H-T right here. A wrought metal, like wrought iron, wrought steel, wrought copper, and so on.
Like hammered or compressed?
Yes, exactly. Think like the old time blacksmiths that would heat up a metal, glowing red hot, pull it over to the anvil, and start hammering and pounding it with their hammer to make a shape. These are wrought metals. Wrought metals are very, very good at compressive loads, but very poor at tensile loads. Meaning, if I need something like a 2-inch square of copper or iron or something, and I'm going to put a hole through that, I'm going to, clamp and I'm going to use copper here, right? The big copper terminals coming off of the transformers up on our power poles, right? They were clamping these big, huge transmission line power lines to, right? Well, those are going to be what do you call it? Those need to be wrought because I've got this big, huge 1/4 inch or 1 inch diameter bolt that I'm clamping this big cable down to. So I'm going to use wrought, I'm going to use hammered. But if I start taking that same wrought metal and trying to bend it like around a radius or around a corner, it will snap or fracture very easily or much easier than an electrodeposited or annealed. So if wrought coppers are heated and hammered, that means we've compressed and pushed that crystalline lattice structure very close together. Then we have annealed metals. So what does it mean for a metal to be annealed? Ooh, stumped
Well,
everybody
the
on that one.
opposite, heated, spread out, relaxed.
Yes, Roshan, you are correct, Roshan. Yes, annealing is the process by which we take a metal, raise its temperature to a temperature greater than 1/2 of its melting temperature, and hold it at that temperature for some duration of time sufficient to allow the crystalline grain structure to relax and spread out. Annealed metals therefore soften and become very malleable or pliable or flexible. These are very good at tensile loads, bending loads, where they can bend and stretch without breaking. However, on the other hand, under compressive loads like bolting actions, they are very soft and will now deform under compressive loads. So very good at tensile, very poor at compression. Wrought coppers are very good at compression, very poor at tensile loads. But in both of those cases, you have to start with solid materials, solid metals, right? Where electrodeposited, you can start with the metal dissolved in a liquid state so it can be deposited ion by ion, atom by atom, molecule by molecule onto the surface to a given thickness. It's kind of halfway in between. It's not as compressed of a crystalline structure as a wrought, but it's not as relaxed of a crystalline structure like annealed, and therefore it's somewhere in between. It is a very vertically tall structure, um, as opposed to a uniform structure, so it does have a few things, but because it's used in a rigid board, we are basically relying on the structural integrity of the rigid board substrate to act as the support so it doesn't see bending or compression, excessive bending or compression. Now, so far, we're talking about the coppers, but we can also order our board with nickel coating. We can order our materials completely unclad. For example, if we want to have a dummy core where we have just completed cured core material with no copper on it at all, we can order it from the laminate supplier that way. We can also order aluminum. We'll see that often in like aluminum core boards where we either need for heat dissipation or mechanical structural integrity beyond what the board itself can give. We can do an aluminum core board. We have X, which is the AA bus as agreed between the user and supplier, and other exotic materials like copper invar copper, copper electrodeposited, etc., etc. Now, once we've chosen our material type, now we need the material thickness. Now, the table in IPC 4101, this is table 1-2 right here, this describes the nominal thicknesses for copper, aluminums, the specialty, the copper invar coppers, the nickels, and so on. Those will have slightly differing thicknesses here because the methodology employed to define the thickness was historically done as a weight per unit area. So I'm sure we've all out there heard about, 1 ounce copper, 1/2 ounce copper, and so on when talking with the fabricators. But what does it really mean for it to be a 1 ounce copper? Well, 1 ounce copper means 1 ounce per square foot. And what that means right here is that knowing the density of copper, if I have 1 ounce per square foot, that in turn equates to a given material thickness right here of 1.35 mils. Now, newer materials that are ultra thin, they have gotten away from the weight per unit area definition and instead gone directly to a thickness definition in the microns. Well, that's the ultra thin stuff. That's the 12, 9, and 5 micron here. But in all the others, we're talking weight per unit area. So when we talk 1 ounce, we know the thickness of 1 ounce in copper because of the density of copper, but because of the density of, say, aluminum or nickel or so on, the same 1 ounce material would have a different thickness. So again, that is a discussion to have with your fabricator. Now, here is the critical thing to note right here. This thickness that we define right here in this table 1-2 of 4101 here, this is actually a nominal thickness, right? So remember that with everything in reality, there is always going to be some amount of tolerancing from the fabrication process at both the fabricator who made the metal themselves, the isolas and Nelcos and so on, as well as a tolerance during the fabrication process at your board fabricator. So this thickness that you see listed right here in the 4101, this is not the actual thickness you are going to receive for your copper if you take or request your microsection analysis, your first article inspection analysis, or however you want to define it there. This is not what you will measure when you measure a board that's supposed to be 1 ounce thick. You are going to measure closer to a thickness of, say, 1 mil thick, all said and done, and we'll see why next week in manufacturing of why that is. But just know that this right here is a nominal thickness for 1 ounce copper, not the final finished thickness of the 1 ounce copper right here. Okay. Next, we have the dielectric thickness that'll be listed. Again, this is a nominal or minimum listing. As we said, due to the method of bonding one material to another using an adhesive, there must always be some amount of surface roughness. So again, another little side tangent here. Can anybody out there explain how adhesive resins actually bond two surfaces together? Yes? No? Anybody out there? We're going to get into this again next week in manufacturing. But suffice it to say, in order for adhesives, whether that's super glue, Elmer's glue, the sticky backing of duct tape, epoxy, urethane, acrylic, it doesn't matter. They all work exactly the same way. In their liquid state, they look for little nooks and cracks and crannies in this surface imperfections or surface roughness here. And when they harden or cure, that hardened resin now has effectively a hook and eye or a mechanical interference to the structure of the other material. This is how all adhesive bondings work. Adhesive resin bonding works, no matter what type it is. And in order to make that work, the surface of our metal must therefore have a roughness. If I have a perfectly glass or Teflon smooth surface, no adhesive bonding will occur. So when we look at the one layer of metal here, the other layer of metal here, the metal will have a non-uniform or rough surface here. The fabricator or the laminate supplier will then measure peak to peak here and report that as minimum, valley to valley, report that as maximum, and will often report a nominal. We are going to be most concerned with this minimum here. This is our absolute worst case for dielectric isolation or electrical withstand or dielectrical performance, and therefore this is going to be the area we care about the most, or the dimension we care about the most. Okay. Electrical strength. This is going to describe the electrical insulative property of the material. That's going to be defined in volts per unit length for the material. So an isola material might have an electrical strength of, say, 1.4 kV per millimeter, right? Or something like that, which basically says for every millimeter of thickness of the material, you can withstand 1.4 kV before you get a breakdown, an electrical breakdown, and arc over through the material. We will actually rely on these electrical strength definitions quite a lot when we design our stack-ups in order to overcome or mitigate some of the statements said in our 2221 voltage chart, especially when it comes to Z-axis. The next one is permittivity. We should all know this one by now. The other term for it is dielectric strength or dielectric, not strength, dielectric constant. So dk or epsilon sub r, depending on whether you talk to engineers, they're going to talk permittivities. If you talk to manufacturers, they're going to talk dielectric constants, right? It's used to define signal propagation on a transmission line, and it's a parameter used in the calculation of transmission line characteristic impedance. It varies with resin content in a particular resin system, and we'll also talk a few more things here. Varies with frequency, resin content, and construction. Where resin content, that is a term that we use, it refers to the percentage of the layer that is the resin. I explicitly say epoxy here, but it really should be any resin, whether that is epoxy resin, acrylic resin, polyimide resin, cyanate ester, butyl acetate, whatever your resin is of the layer, phenolics, etc. Whatever resin you select, the most common that we talk about is epoxy. So the percentage of that layer thickness that is epoxy and not the actual woven glass. The higher the resin percent, the lower the dielectric constant, the better the electrical performance. And construction, we're going to talk about that here in just a minute. Also, it is possible to have a large variance in resin content slash electrical permittivity or relative permittivity here for a given material thickness within a given resin system. My recommendation is to always spec the thickness and the construction for each layer, or at a bare minimum, spec the parameters. Spec the, here and I'll say, thickness, R, F, which we'll get to later, C. Basically, if you don't want to spec a thickness and a construction for each layer, at a bare minimum, guide your fabricators to your decision by saying, well, my layer needs to have a dielectric constant of this, a dissipation factor of this, a resin content of this, et cetera, and a thickness of this, which will effectively tell them they have to pick the ones you want without actually specing it that way. But you should always spec thickness and construction for each layer. Then we have chemical things, such as the glass transition temperature. You've heard me talk about this before, especially if you're coming back from PCB1. Glass transition temperature is the temperature at which the resin changes from a solid into a viscous gel. The material properties are different above and below the T sub G value, and T sub G is an extrapolation of the linear regions of the curve. Notice here that I have below this T sub G value, I have a portion of the curve here where I can have a fairly large change in temperature for a fairly small change in thickness or dimension. And above T sub G here, for a very small change in temperature, I can have a fairly large change in thickness or dimension, I should say right here. So now I have these two relatively linear regions of the curve right here. And then of course I have this non-linear region. This is where the material starts changing properties or going into its phase change, right? At this point right here, I am changing from a solid into the liquid state right here. And when I start going through the phase change, my material properties become very non-linear right here. If I take the two linear regions and I extrapolate their linear behavior, the point at where the two linear regions cross, the two linear extrapolations cross, this is what we will define as glass transition temperature, or T sub G. However, T sub G is not a magic number where everything is perfect below that and goes to chaos above that. Instead, it is just a property of the material. It is recommended. Now, this is my 30 years of experience recommendation. you are free based off of your own risks that your organizations are willing to accept, as well as the safety requirements and of your material and your products and so on. But my recommendation is to always have approximately 50 degrees C delta between glass transition temperature and the maximum operating temperature of your product. So for example, if you are building products for the consumer segment where you only have to have products that work are designed to work up to 70 degrees C as maximum operating temperature. Well, I could use pretty much any material I wanted, lower cost materials that maybe have a 120 or a 140 or 150 degrees C glass transition temperature, the older, lower cost materials. On the other hand, if I'm designing for military, aerospace, or even medical where I have higher reliability, well, let's just take military aerospace. The typical mil aero operating temperature range is minus 55 all the way up to plus 125 C. So if my maximum expected operating temperature of my product is 125, I'm going to say I want a material whose T sub G is 175 or higher. I might accept 170, that's right on the edge, but I might want to go a little bit higher, 180 or even a 200 degrees C. There's also another temperature that is now spec'd in our 4101 called T sub D. This is called the decomposition temperature. There's not really a chart for it. This is really a temperature that goes back to our chemistry classes from university. This is the temperature at which the material decomposes into its base elements. With T sub G, if I exceed T sub G with my material, the epoxy is still epoxy, the glass is still glass, etc. As soon as I cool it back down, it shrinks back into the normal size. On the other hand, if I exceed the T sub D or the decomposition temperature, which for a material that might be like a 170 C board material, the decomposition is typically up in the 340, 350 degrees C range. Very, very high temperature. That is the temperature at which the epoxy carbonizes and breaks back down into ash and carbon. The glass is turned back into silica, and so on and so forth. Basically, once you go past decomposition temperature, the board's not a board anymore. It's a pile of ash and carbon dust and so on. Yes, Mattia.
So, can we then say that, let's say, the mechanical properties are affected when we are getting close to the T sub G, or are also the electrical properties affected?
Depends on the parts you've selected. So, for example, well, let me qualify it this way. In theory, pretty much all parts on the market are not designed to work up to the T sub G of the board, right? Most components out there have a max operating temperature of, say, 85 or 105 C. If it's a mill part, 125 degrees C. You might get 150 degrees C, right? But if you build a board with commercial off-the-shelf parts for, commercial temperature range, 70 degrees C or 85 degrees C, and you start taking those parts up to 100, 125, 150 degrees C, yeah, they're going to be affected. But in theory, your board should never get there unless you're military. And if you're military, you're selecting parts that also are rated to those kind of temperatures and so on. So it all depends on the parts you put on your board, Mattia.
No, so the reason why I ask is because we often need to do, let's say, H-toll boards or HAST boards where let's say if the device needs to work up to 125, we need to heat it up to 175 to test some things. And then I'm really wondering which material we should be choosing, and if we are choosing something which is, let's say, it has T sub G of around 175, if it is just a matter of mechanical stability, or if it also would change, let's say, what we have with reflections, because we often have relatively high clocks and stuff like that signals.
So HALT and HAST, your accelerated life stressing and stress screening, right?
Yeah.
So where you're going up to those elevated temperatures, that's where you're looking for those problems. Now, will they cause problems? Potentially. Will they cause reflection problems? Probably not if you've designed your board well, unless you're in the RF world, where your fundamental clock frequencies are in the multiple gigahertz or double-digit gigahertz or higher frequencies. In those cases, yeah, the expansion from the board itself might be a problem. Normally, you're looking at mechanical issues. The issue you're going to be running into, though, with like digital and standard analog systems in those higher temperatures is the parts themselves becoming unstable. Op amps, clocks, not clocks, your digital chips, right? Your FPGAs and so on start operating in an unstable condition, right? An unknown unstable condition. What that's going to do to your system, I don't know. That's why you're doing the stress screenings and stress testings. Right?
Okay, thanks.
Infinitely varying possibility of what could happen. You could have your, the accelerated testing could cause your FPGA to have a improper output state change, or maybe not go high enough on output state change, and so you get an unknown race condition. All kind of problems could happen with those highly where you exceed the expected max operating temperature of the parts. Most often it's in your R's and C's, right? Your resistors, you go that high in temperature, your resistor now changes resistance value based off TCR, right? And now what was a stable corner clock frequency or filter frequency is not. Or you get a larger voltage drop across the resistor, and so on and so forth. So that's the whole point of halt and hast.
Right. So that is actually what we I think we're seeing, because I think that at 175 also resistors were not terminating as they were supposed to be terminating anymore.
Yeah,
Okay.
You took your poor little 22 or 33 ohm resistor, and now it's like 50 ohms or 60 ohms or whatever it is. It's like, well, it's doubled its resistance, so now I've got all kind of crazy things happening. Yeah.
Yep. Okay, thanks.
Exactly what I would expect to start seeing, kind of things. Great questions. All right, let's keep going on here. Loss tangent or dissipation factor, that DF that we talked about. Let's see here. Mati, I'm going to lower your hand because I suspect that's the same question you already asked, or you already lowered your hand. Okay, good. Okay, loss tangent or dissipation factor, tangent delta or DF. Okay, officially the technical definition of loss tangent is ratio of total loss in a material to the IR product of a capacitor made of the same dielectric material. That is a very engineering, scientisty, chemist way of trying to state what loss tangent or dissipation factor is. Let me see if I can break this down for you so it makes a little bit more common sense here. The higher the loss tangent, the more energy is lost in the material, and the slower the signal must be to travel down the material, or basically travel down the conductor. Conductor in the material. Okay, so this gets into in the RF world where we talk about skin effect and so on. But basically, what we're talking about here is that when we have a high loss material, we can think of this in mechanical terms, spring force or dampening factors, right? If I have, and the analogy I like to use is when you all out there were kids, did you ever take the rocks and throw them in the puddle of water, right, or the lake or whatever, and watch the ripples transition down away from where you threw the rock in the water? Yep. Yes. No. Everybody seen that at some point or another?
Sure.
Okay. Now, where I grew up, we had lots of mud puddles too, because I grew up in very, very wet, rainy area of the United States. Who here ever threw rocks in puddles of mud to see how it splashed in mud? Or am I the only crazy one like that?
Well, I was throwing rocks in mud, but not to look at the splash, or not to observe the splash, but there was a splash. Yeah.
Okay. Throw the rock in the water, right? How many ripples you get? 5, 6, 7 ripples, right?
Yeah,
like
right.
that. How many
Right,
ripples do you
right.
get in a puddle of mud?
None.
Come on, maybe
It
one.
starts
If
and,
you're
and it
lucky,
goes
yeah.
away, yeah.
Yeah, if you're lucky, you get one ripple, bleh, and then it just stops, right? Mud is a high loss material. It absorbed all that energy. It dissipated that energy into the surrounding material of the mud, right? The rock is our signal and our conductor. In the water, the energy traveled much further before it would dissipate. Yeah. It's the same effect here. If the material, the resin and glass surrounding our conductor is of high loss, then some of the energy of our signal as it travels down from the driver to the receiver, some of that energy is absorbed and dissipated into the surrounding medium of the material of our board. On the other hand, if I'm a very low loss material, almost none of that. So basically, the harder and stiffer that the material is, the lower the loss tangent, or less of the energy is lost, and I can run my signal at a much higher frequency because now with skin effect, all of that energy will be out at the surface and available to be absorbed into the surrounding medium. Whereas if I am in a high loss material, I'm going to need to run at lower frequencies so that more of my energy is contained in the core of my conductor and therefore can travel down my conductor and still get to my receiver without having significant signal degradation. Now, similar to the dielectric constant, the dissipation factor here is also going to have some things it varies with. It will vary with frequency, it will vary with resin content, but now it also varies with temperature and humidity. Just like we were talking about with the glass transition temperature, as the board material gets hotter and hotter, that resin starts to soften up. It tries to go back to phase change. When it's fully cured, it'll never go completely back to phase change, back into the liquid state, but it does soften. The softer that resin is, the more it will dissipate or absorb energy. It'll have that spring force, right? Same thing with humidity. If we've ever had a material that's gotten moist and humid, think cardboard boxes, right? A cardboard is a somewhat rigid material when it's dry. When it gets wet or damp or absorbs moisture, it turns goopy spongy, right? Same thing here. If our board is allowed to absorb humidity or increase in temperature, the dissipation factor, otherwise known as the loss tangent, will increase and therefore more energy will be dissipated in the surrounding medium of the board. Next, we have the flammability rating. This is provided by UL, specifically the same UL or Underwriters Laboratory, at least for those of us here in the United States. And I'm sure overseas folks have similar safety or governmental compliance organizations. But here in the United States, we have Underwriters Laboratory. They're a big, huge national laboratory that tests all manner of materials and products for safety and then puts a little white tag on them that says, this has been tested and certified by Underwriters Laboratory. We have little white tags on our pillows, on our mattresses, on our blankets, on our every electrical widget we've ever bought has a little white tag on it that says, you know, tested for compliance to a certain UL safety standard and so on. Well, because they're testing for safety, one of the safety things that they test for is flammability. In this case, it's Underwriters Laboratory certification number 94 or standard number 94. So UL 94. There are three key test conditions they're going to try for here. Or the two test conditions are vertical burning and horizontal burning. We are primarily going to be concerned with horizontal burning. That is going to be our best test. And only if our material cannot survive any of the vertical burning tests, they'll then perform the horizontal, where it'll get a rating of UL 94 HB for horizontal burn. But in the vertical burn, there is a test apparatus right here. There is a Bunsen burner type device. There's some cotton or surgical cotton down here. There are very prescribed dimensions of the burner, the size, the diameter, the size of the blue part of the flame, the size of the orange part of the flame, the size and shape of the specimen of the material to be tested. And basically, it's like flicking a lighter on it. They literally just keep flicking, turning the flame on, turn the flame off, turn the flame on, turn the flame off, and see if the material will burn. And if it does burn, will it self-extinguish? So in order to get their best rating, a V0, which a lot of our board materials will get, the material must extinguish within 10 seconds of each flame, 50 seconds after 10 flames, and have no dripping particles and no glowing combustion 30 seconds after the second flame. Slightly worse rating is V1. Same conditions as V0, but longer times. 30 seconds each flame, 250 10 flames, 60 seconds after the second flame, no dripping particles, no glowing combustion. V2, slightly worse than V1. Same times as V1, but now allows for some dripping particles. So some little burning embers of the material can be falling off and still burning and get down to that surgical cotton and light that stuff on fire. So again, now certain materials can't even survive the vertical. Think like some synthetic fabrics, nylons, rayons, and so on. That you put a flame to that stuff and it just goes up like a fireball, whoosh, and the entire, shirt or whatever is gone. Okay. So in that case, they'll do a horizontal burn where they'll hold the specimen horizontally over the flame and see if it'll burn just a hole in it or if it'll continue to burn sideways. But here, the flame is allowed to grow up the specimen this way. So again, this is our flammability rating right here, and this is given by UL. And V0 is always going to be our target we strive for, especially if we are in any kind of high reliability, such as medical, automotive, military, aerospace, et cetera, et cetera. If we're in simple, giveaway consumer goods, we might allow a V2, freebie giveaway swag or things of that nature where we're a little less concerned. All right. Okay. This is a great place to take a break. We will come back and we'll try to finish up the slides here. I will stay online if anybody's got any additional questions. Oh, real quick before I go on break, I did put an announcement in our course announcement page. Hopefully everybody saw that. So basically, if you remember last week, I mentioned, you might have seen that we had some duplicate standards, the DRM standards in there. We had the old version, the old rev and the new rev. We have since cleaned those all up. And what we're asking everybody to do is just in the same way that you went and confirmed that you have your Altium licenses all up and working, before we get to the end of the course and we use our standards when it comes to the exam, we would like everybody to make sure that you're able to download and open the standards, that your DRM credentials are working. And if they aren't, again, please send an email to the Education 2 and copy myself. And just let us know whether you need your DRM credentials reset, if you're having any issues, and like that. We just want to make sure that you have access into all of those standards that we provided before we get towards the end of the course. So if everybody could do that this week, we would greatly appreciate that. All right, and with that, let's take like, I don't know, 10-ish minutes or so, 12-ish minutes. We'll be back at the 15-minute mark. And we'll go from there. And again, I'll stay online if anybody has any additional questions.
Hey Chris, I know you've already told us, but the credentials used to access the DRM documents, is that the same that we use to log into the IPC Edge?
No, that would have come from Ivan. You would have gotten an email, but I will show you. There's also an area in our Edge page where you can actually find those. So let me go ahead, share my screen again, and I will show you right here.
I
So you
apologize.
should
I know
have
you've told
received
us
an
already.
email from Ivan. But if you did not, if you go over here to our Edge page, down here, at the very bottom, it says DRM access info. It looks like a item submission area right here. When you go in, you'll just see your feedback, and it'll have a single line. And over here in the feedback area, you'll see it populate with your specific username and password that you have.
Okay, I see. Thank you.
No problem. Great question. Okay, are we all back from break?
Here.
Yep. All right. Excellent. Let me go ahead then and let me get the share restarted here. And we will continue on. And for those that have already seen the announcement I posted, we made a minor update to that. If your DRM credentials are already working and you're okay with those, there's no need to send us a verification email. Please just send us an email if you are having issues with your DRM credentials. All right, with that, let us go ahead and continue on right here. So what is the material that we're going to use for our boards? This is the one and only time in this entire course that I'm going to refer to it this way. FR4. FR4 is not, has never been, and never will be a direct specific material definition. Under ANSI/UL, there is an FR4 specification. It's actually an ANSI specification number, but it too requires the use of slash sheets. IPC and has defined the 4101 with the slash sheets. And the term FR4 originally was defined by the NEMA organization, and it simply defines a flame resistance or flame retardant grade 4. There are actually several different styles of FR rating. There's FR1, FR2, FR3, FR4, FR5, and beyond. What do we mean, however, as an industry when we ask for an FR4 material? What we are assuming is an epoxy-based resin, a woven glass reinforcement with a flame retardant, and a UL 94 flammability rating that we just saw. However, there are many, many different formulations and many different electrical properties. And from IPC's point of view, FR4 is not a material specification. It is used in industry as a standard term. It kind of gained colloquial acceptance over time. So when you say that to a fabricator, you want FR4, you will get a material that's FR4, but the behavior of your board may change build to build depending on what they have in stock. Because as we will see, there are many, many different formulations and properties. You actually need to spec the IPC slash sheet for the specific formulation that is desired. What do we mean by these slash sheets here? So the slash sheets are one or more pages within the 4101 spec, and they start with a header of the slash sheet, which will describe the resin system. We'll go look at one of these in a little bit more detail, or actually I'll just zoom in on one to show you what some of these properties are. So the header of the slash sheet, and we call it a slash sheet because the entire specification for this unique material definition is IPC 4101/126. It has woven e-glass for the reinforcement. Its primary resin system is epoxy, with the secondary being a multifunctional and the first secondary and the second secondary being a multifunctional or even non-epoxy. So slash 126s can have up to 5% of their resin a non-epoxy polymer or other material. The majority of it is going to be a multifunctional epoxy, as opposed to a bi or difunctional epoxy. It means a multifunctional. We're going to have a flame retardant using a RoHS compliant bromine formulation. This one will contain the inorganic fillers. And again, under UL and ANSI, it was called FR 4.0, but still /126. So yes, in the alternate specification world of ANSI UL, it had that rating system. But if you just say FR4, it's like saying, I want an IPC 4101 material. And as we'll see here, if not today, we'll see on Wednesday, there are many, many different formulations to this material. It will also be a 170 degree C minimum T sub G, and it will be a UL 94 V0 rating. Again, we will also see that just like the data sheets that we're going to get for our electrical components, there will then be a bunch of quantified, or the body of the slash sheet quantifies the properties of the resin system itself. Definitions such as peel strength, standard profile copper foils, volume resistivity, surface resistivity, moisture absorption rate, dielectric breakdown, permittivity, loss tangents, flexural strengths, minimum flexural strengths at elevated temperatures, arc resistance, thermal stress. Here's that electrical strength we talked about, 30 kV per millimeter here, flammability rating, glass transition. Here's that decomposition temperature I was talking about, and so on. So you'll see these. Now, one thing to keep in mind, okay? This particular system here, or this data sheet or slash sheet as it were, this is going to describe the absolute minimum requirements. As long as a material meets or exceeds these requirements that are stated on the slash sheet, the material can list itself as a 4101 as a slash 126 material. So as an example over here, let's go look at isola laminates. Okay, so I'm going to go down here and I'm going to go to the advanced search and show the options, slash sheets here. Now I'm going to say, show me the 126 materials. And I'm going to pick this 370 HR material right here. And I'm going to go look at its data sheet right here. Now, isola certifies that this material, and they have to go through independent third-party contractors like UL in order to get this certification. Right here. Let me zoom in on this. All right. Glass transition temperature, right? The slash sheet set need to be 170 minimum. This particular material is a 180. Permittivities, however, if we looked at the slash sheet itself, it said the permittivity should be between 5.2 and 5.4 at the 1 gigahertz, 5.2 at 1 gigahertz, 5.4 at 1 megahertz, and so on. Where isola is saying their 1 gigahertz is closer to 4.17. Radically different dielectric constant compared to what's on the slash sheet, but this is exceeding. The lower the dielectric constant, the better the performance of the material. So as long as their material does not exceed that 5.2, 5.4 number, we're fine. Same thing here, dielectric breakdown, right? Or electrical strength. It's at 30 kV per millimeter. This one's rated as 54 kV per millimeter, and so on. So we can see that this material is actually far superior to what is listed on the slash sheet. So the slash sheet is a starting point minimum, but this is why I said previously, constructions or at a minimum specify all the parameters you want. Exactly what dielectric constant, exactly what electrical strength, dissipation factors, and so on. Now, I'm going to point out one more thing, and I may have shown you guys this already. We'll go back over here. Not only does the master data sheet have a difference of parameters and performance over what we see on the slash sheet, but even on the data sheet, This dielectric constant here at 1 gigahertz, that is an average number. Okay, that is, they took all their different formula, all their different constructions, took an average and said that's what we get in general. What you really need to do is look here. So let's look at the cores. So there's usually a table like this, a construction table, cores, and the individual prepreg sheets right here. So I'm going to look, I like to use this range right here. If I want to have a layer that's, say, 3.5 mils thick, and so we're looking at this one here, thickness in inches, 0035, 3.5 mils thick right here. We're also going to note that the third column here is my 1 gigahertz number right here. There's my 4.17, there's my average, good place to start. But that's a 51% resin content because it's made with a single sheet of 3313. We'll look at that more. If not today, we'll look at it on Wednesday if we have to follow up on Wednesday. Okay? However, I can achieve the same core thickness of 3.5 mils by having the laminate supplier fabricate that out of 2 sheets of the 106 material. Right here, where now I have a 6.8 or 68% resin content as opposed to the 51. And you notice instead of a 4.17, I have a 3.86 dielectric constant, a far, far different from a signal integrity point of view performance compared to the 4.17. So if I just use the 4.17 for all layers, again, my performance is not going to be what my equations tell me. My actual performance is going to be different because they might build it out of this instead. Okay, and this is just within one resin system. So when we say a resin system, we mean this. 370HR is a resin system because it contains the 370HR resin plus the sheets of woven e-glass, so we call this a resin system. If I were to go back and pick one of the other materials that also claims to meet the slash 126, I might get even more difference of performance. So I usually go so far as I say, I want this board built out of Isola 370HR and so on. But again, that's going to be up to you and your organizations of how you wish to handle that. But this is basically what a slash sheet is. It is these descriptions right here, right? So it describes the resin system and it describes the basic quantified performance. It's just like a data sheet for a resistor or a capacitor or anything else. Okay, again, this is a more high-level grid from the same Isola people. This is the older way their web page used to be. I showed you the updated version right here. Within a single resin system, you get large variances in glass weave and resin content. IPC 4412. This is not one of the ones we provide to you. This is going to be 3 levels removed from you as a designer. 4412 is going to define the requirements of the woven glass itself. This traces its origins back to the actual textile industry for woven fabrics. Just because the yarns and threads that we're using in our fabric are glass instead of cotton or wool, it's still woven fabric, so we're still going to follow what we have in that type of system here. I'm also going to go over here and I'll show you what that is right here. If it'll pop up. Maybe it'll pop up. Thinking about popping up. But effectively, this is where those numbers are going to come from. 106, 1080, 2113, and so on. These are going to describe a specific sheet of woven material. Okay, I guess it doesn't like. We'll just go to it from here. That's fine. Sorry, gotta go get this open. 4412. Now there's other specifications for the other woven materials, the woven S-glass, the phenolic papers, and so on. But 4412, that's the one for the woven E-glass, which is the primary one we're going to use. Again, the first half of the standard is going to describe, for example, the electrical grade of the glass fiber. So what are the various constituent elements of that make up the glass, and so on. So it'll go through several of these different standards right here. What are considered defects, the SI nomenclature, et cetera, et cetera. Well, what we're really going to be concerned with is down here is the definitions right here. So that's SI. I'm going to go to the US system right here. So when we say 106, what we're really talking about is a sheet of material that has a wrap and fill of 56 by 56 wraps and fills per inch using this yarn style right here. I'm not even familiar with what the D900 1/0 by D900 1/0. That describes the individual diameters of the glass yarns that make up the threads, that make up the fabric, etc. What its nominal weight is, the weight tolerance, and that's ounces per square yard, and so on. I believe that's what it is. And the nominal thickness for reference only for 106 is 1.3 mils. Now you'll notice back here when we were in Isola, we go back over here to the constructions right here. If I go look at a sheet of 106 prepreg, it says its nominal thickness is between 2 and 2.4, depending on which how much resin they put in there. But it says that on the 4412, it says that it's 1.3, and that's one of the things to understand. When we talk about these materials in the resin system itself, as we said, it's the sheet of woven glass impregnated with resin. So basically, we're taking the sheet of pure woven glass, coating it with the epoxy resin, and partially curing it to where it's flattened. And now what we have is the material thickness from here starts out at 2 or 2.4 mils thick, and then that resin is allowed to soften, and then under hydraulic pressure, which we'll see next week, flows around our various different copper features on our different layers to form our bonding. Okay, so what we end up with is the sheet of 106 material is going to be thicker than the sheet of 106 glass because it's the glass plus some resin of our resin system here, if that makes sense to everyone. But anyways, this is where those numbers come from. So when you talk to a fabricator saying, hey, and your fabricator asks, I'm recommending that we make the board out of, 2 sheets of 106 instead of a single sheet of 2113, this is what they're talking about. It's those numbers describe from the woven glass manufacturers the actual size, the size of the threads, the size of the yarns, the number of yarns per inch, the wrap and fill, all of these things that trace back to the textile industry to describe a sheet of woven material. Now, the reason why we did not give you, as part of this class, access to this spec, as I mentioned, you as designers are 3 levels of decision removed from that specification. You as designers are going to design a stack up. You will then send that stack up to the fabricator. That's level 1 of removal. The fabricator will then request material from a laminate supplier like Isola. 2 steps of removal. Isola, in turn, the supplier of the laminate itself, will then specify the sheets of glass or the woven, glass fabric from the glass fabric supplier. So 3. So you are 3 steps of decision making removed from needing to read the actual 4412. I just want to pass that information along, show you that it exists. Again, my opinion, everybody in the board design industry should have every one of the IPC specs just to have a complete library. But that's just me. I like to read every possible spec there is. But the reality is, you as a designer don't necessarily need to know the minutia detail that's in the 4412. only what the implications of those are, which we'll talk about next week and during signal integrity as to what impacts those are going to have on your ability to design. But this is now you'll be able to have some understanding here, though, when we look at things up here like that 3.5 mil thick right here. One sheet of 2113, one sheet of 3313, or two sheets of 106. So now you can see the difference that the laminate supplier went through to all achieve a core that was 3.5 mils thick by applying different amounts of heat and different amounts of hydraulic pressure of their base materials before they applied their copper. So in this way, you can see the various different why they have so many different constructions. And it says what sheets of prepreg material, which are meaning what sheets of glass with resin, did they use to make these layers. Any questions on this before I move on to the next topic? You know, this gets a little deep into materials here. Any questions on this before I move on? Yes, Kevin.
So from this spec sheet that we're looking at on your screen versus the sheet for the fabric glasses in the US system on the IPC standard that you said we don't have access to. If you scroll up to the 106 for a second.
That's a core, so you're talking about the prepreg itself, which is down here.
Okay. So this one was thicker.
Right.
And that's because you're saying that it's accounting for the resin content as well as the glass.
Correct. So I'll draw it for you.
So I know there's like a standard while you're drawing. There's a standard that talks about I think it's in aerospace that usually the dielectric layer after the first layer and between the first and the second layer has got to be a minimum of like 3.5 mils. Oh,
it's
is
not
that
that it
accounting
has
for?
to be.
Yeah.
What IPC says is when you as the designer do not specify it, that's the minimum they will use. That's at least what's in IPC. Now, different military aerospace that might come from, you know, like US DoD or, you know, European Space Agency or whoever, they might have their own standards. But from IPC's point of view, that says when not indicated on the master drawing, minimum dielectric thickness shall be, and I believe it's 3.9 mils because it works out to the metric equivalent converted.
And is that that's accounting for the resin and the glass?
Yeah, that's just saying the
okay.
total thickness of between the two copper. If you measure between the two copper, what is that total thickness? Now these numbers here, the 4412 versus what we just saw in from the manufacturer or in the 4101 is if I have a woven glass material here, I then have to impregnate that with a resin, but that resin needs to fully encapsulate the glass. I cannot have any glass exposed except maybe right at the end when I cut it. So this thickness here is from the 4412 right here, and that might be that, you know, 1.3 mil, where this overall thickness, glass plus resin, that's from the 4101 slash manufacturer, and that's supposed to be an M right there, and that's where we might get the 2.4 because it's the 1.3 plus resin. Does that make more sense to you now?
Yeah, that makes a lot of sense.
Okay. Excellent. Great question. And then Mattia, it looks like you had a question out there too. Mic's open, or was that just your mic still open? Okay. I'm going to assume that's a mic was just open. Okay, let's keep moving on here then.
Oh, I had one more question, if that's
Oh,
okay.
sure, Kevin. Yes.
Yeah, I was just wondering, and apologize if you've already covered this. The difference really between the core and the pre-preg. I've always struggled to understand when to use which and building a
You
stack up.
always use both, at least for these multi-layer boards. You always use both, and we're going to get into this more in the manufacturing week.
Okay.
Okay, but I will draw a quick little sketch for you here. So I'll start with a assumption out here. You are familiar with resins of any kind, right? Like epoxy, super glue, Elmer's glue, whatever, right?
Correct.
Starts in a liquid, you put it on something, you let it dry, and once it's dry, it never goes back to a liquid, yes?
Mm-hmm.
Okay. The same thing is happening here with our boards, okay? So I'm going to start here, and I'm going to do 4 layers. I'm just going to do 4 layers. The blue is going to be my copper layers. Probably should have drawn those in orange, but whatever. That's the last color I was on. Okay. Now, core. Cured. Pre-preg. Partially cured. Resin. And become liquid. Okay. Now, if I want to glue these 4 sheets of copper together, first off, and we'll get into this next week in processing, I have to process my layers in pairs. Okay? Meaning I can't just glue all solid copper together and then somehow etch all of my traces and features. I have to pre-etch the features on the inner layers, right? Go through the etching or form the traces and pads and stuff. No holes yet, but I have to form the traces and pads and so on all the inner layers. Then I have to be able to glue everything together and then form my traces, drill my holes, plate, and so on for my outer layers. So there's 2 ways I can do this. I can put a core right here, and then a pre-preg here, and a pre-preg here with foil here. So my core right here, this would be think of it as a very, very thin 2-layer circuit board to which I can then etch all of my features on, and here's layers 1, 2, 3, and my pen's not working very well. So 1, 2, 3, and 4. There's my 4 copper layers, right? So I would etch the features on layers 2 and 3. Think of this as a very thin board. I would then put pre-pregs here and here with sheets of foil of copper here and here. Glue everything together. So the pre-pregs are going to be my glue sheets. The cores are very, very thin 2-layer boards. So I'm always going to alternate a core, a pre-preg, a core, a pre-preg. That way I can glue the whole stack together when I'm ready to do my lamination. Now I can reverse this, and we'll talk about this during fabrication. I could put a core here, and a core here, and a pre-preg here. That would work, but that second option I just did in green, that is a far more expensive process and far more risky process for the fabricator because, and we'll get into this next week, the 2 outermost layers, layers 1 and 4, have to be etched separately from layers 2 and 3. And I would have to process the first core and the second core separately to etch their two inner. Then I'd have to glue. Then I would have to laminate the whole thing together. Then I'd have to drill and etch the outer layers. So while it can be done, it not as good of an idea to do it this way. So we always start foil, prepreg, and then we just alternate prepreg core, prepreg core, prepreg core, right? Because the prepregs are going to be the glue, and the cores are the thin 2-layer boards that are going to have all of my inner copper features on them before I glue my layers together. Does that make a little bit of sense to you, Kevin?
Yeah. Yeah. Thank you.
Yep, not a problem. Great question. Okay, now, speaking of the weave pattern, we were just talking about, the wrap and fill per inch in the 4412. What we're going to find when we get to signal integrity is that the thinner sheets, the thinner layers with the higher resin content, do far superior for us from an electrical and a signal integrity point of view. However, as we go thinner in our layers, because there's less material of the glass for the wrap and fill, what we end up with is a pattern similar to very cheap fabrics, right? If you've ever gotten like a concert t-shirt or, freebie giveaway t-shirts or things like that, you'll notice if you look at it through the light, you can almost see the holes between the weave, where if you get a very, very, expensive wool or high-end materials, it's very, very tightly woven together. So because of the lower number of wrap and fill per inch on the thinner glass sheets, what you end up with is a weave pattern with holes in between the glass weave. The thicker you go, like the 2116 all the way up to 7628 here, as we get more glass in the layer, so less resin in the layer, we get a more uniform glass coverage. Now, this can cause two problems. We'll talk about this in signal integrity. This can cause both a signal integrity problem as well as an electrical insulative problem. Remember those spikes we talked about back here? Remember these spikes right here? So if I end up with two spikes, and this is, very low probability, but it's a non-zero probability. If I end up with a situation where I have two of these spikes that are pointing at each other, kind of lined up in the copper, and those happen to line up in one of these gaps where there's only resin and not glass, the electrical breakdown is much lower, and I can effectively arc through my layer that's supposed to be insulative. The glass is what gives me the high voltage withstand. The resin, though, gives me the high resin content, gives me the faster signal propagation, the better signal integrity. So what we usually end up doing is to try and get the best of both worlds. Again, when it comes to layer thickness, is rather than one single sheet of thicker dielectric, two thinner sheets of thin dielectrics laid one on top of the other, the probability of the two glass weaves perfectly lining up so you still have gaps is near zero. It's not zero, but it's like 12 sigma, 24, it's way out there in probability that it effectively mitigates that problem. But we'll see that. So this is one of the trade-offs in the processing costs, the material costs, and the performance costs of single thicker sheet versus multiple thinner sheets of the material. Okay. Now, if you need to use single thin sheet and you have the concern about electrical performance or electrical withstand, there is newer techniques. So the industry itself, the people who make the glass weave and or the isolas before they apply their resin, have developed methods. So just like with traditional fabric fibers like cotton, wool, nylon, and so on, we tend to think of those as having a circular cross section. However, unlike natural organic fibers, cottons and wools and the like, where if you've ever looked just like a human hair. If you've ever looked at natural organic fibers under a microscope, especially like SEM microscopes, they actually have a roughness. They have little barbs and hooks and, almost like scales to them and so on. So that once two individual threads come in contact with each other to form the yarn, they kind of mechanically interlock with each other. Glass, on the other hand, being a smooth material when it's extruded like this or spun, effectively these act like little roller ball bearings. So what they've been able to do is through a combination of of hydraulic and mechanical means, basically vibration and water pressure, right? By basically vibrating and putting a little bit of compression on that, they're able to cause these weaves right here. They're able to cause these weaves to spread out into this more uh, elliptical cross section, I guess you'd call it right here, which vastly reduces the size of those gaps. It also makes more uniform glass thickness in the layer. So more uniform glass coverage, more uniform glass thickness. Now, I borrowed this from my embedded resistor design class because there is one other property of our conductive material, our coppers or our copper or aluminum, whichever one we're using here, called sheet resistance. You may have heard this in your physics classes or electrical engineering classes, but all conductive materials, and in fact all materials period, but we're going to be focused primarily on the conductive materials, have a physical property called resistivity, not to be confused with resistance, but resistivity, that is defined by, noted by the Greek letter rho. That's that P with the little squiggle on the bottom of their line right there, rho. It's typically defined in ohms per unit length or ohms length, right? Ohms centimeters, ohms per centimeter, basic idea here. And sources such as MATWEB are useful for looking up these physical properties of the material. For annealed copper, such as might be used in our printed circuit boards or for coppers in general, we're on the order of like 0.0000170 ohm centimeters right here, and that's our resistivity. Using the resistivity of the material, we can determine the resistance of the conductor using equation 1, where L is the length and A is the cross-sectional area. However, for traces on our printed circuit board, the cross-sectional area can be found using equation 2, since we're talking approximately rectangular, ideally rectangular cross-sections of our conductor. So we simply convert area to thickness times width. That gives us our cross-sectional area. Here T is thickness, W is width. If necessary, volume can be calculated using equation 3 here, but we won't need that. Now, putting those two equations together, using the resistance equation, we can determine the special case of a square. So in the case of a square, length is equal to width. Substituting equation 2 back into equation 1 is going to give us equation 5, will give us equation 4. And in the square, L is equal to W, and these two terms will cancel out, giving us equation 5. So whether we have a square of our copper that is 1 millimeter by 1 millimeter or 1 kilometer by 1 kilometer, the resistance across that sheet, if I measure from here to here or here to here, the resistance of that square will always be exactly the same. And it will be given by the resistivity term, that 0.00017 ohms centimeter, divided by the thickness, and that will give us a special case called the sheet resistance, or ohms per square, and that's regardless of the size of the square. Now, once we have that, now that we have the sheet resistance, we can determine a first order approximation of the total resistance of the trace. Right? So now we have that, we can get the first order approximation, or DC, resistance of the approximation of the total resistance of the trace. Using equation 6, we simply divide length by width to get the number of squares in that trace. And it could be fractional. 3.72 squares, 9.66 squares, whatever the case is. You simply divide the total length of the trace by the width of the trace. That'll give you the total number of squares. And multiply the number of squares by sheet resistance, and that'll give you the total resistance of that trace. Okay. All right. With that, I know we didn't get as far as I normally do. There were lots of great questions today, so please keep those coming. I think this is a great place to stop. We will continue here on Wednesday and then jump back into looking at the board design. For those of you, Kevin and Mattia and folks that had some really great questions about the tool and about how we would do certain things in design, please bring those back up on Wednesday, and we will look at those hands-on on Wednesday. But otherwise, I think this is a great place to pause for the day. All right. Any last questions before we call it a day?
Thank you.
Yep, no problem. All right.
Thanks.
Yep. With that, we will call it a day, and I will see everybody on Wednesday.
Thank you. See you on Wednesday. Bye.
Thank you, Chris.